we start the session, sir?
Sure, Professor.
Good evening to all. Today is the fourth day of ATAL FDP. Today we have two important sessions. One is by Dr. Deepan Bharathikan, Assistant Professor, Anna University, Chennai. The other is by Dr. Manoharan, AI Innovation Lead, ISH GCC, Chennai. Before starting the session, please let me introduce Dr. Deepan Bharathikan. We are glad to welcome Dr. Deepan Bharathikan, Assistant Professor at the College of Engineering, Guindy, Anna University, Chennai. He completed his PhD in Production Engineering from NIT Trichy and previously served at SRM IST as an adjacent faculty in NIT and as an adjacent faculty in NIT Trichy. His research expertise includes welding, nitinol shape or memory alloys, metallurgical characterization, and process optimization. Professor Dr. Deepan Bharathikan has published more than 41 journals in reputed journals and 14 conference papers with more than 400 citations and an H-index of 11. He has guided doctoral research in advanced welding techniques and is a life member of the Indian Institute of Welding and Indian Welding Society. His contributions reflects his passion for research, innovation, and students' mentorship. On behalf of you all, I request Dr. Deepan Bharathikan to handle this session, and I welcome Dr. Deepan Bharathikan. Thank you, sir. Professor, you can handle the session now.
Yeah, thank you, Professor. Thank you for the warm introduction. I will share the screen. Please let me know whether the screen is visible so that I can start the session once again.
Yes.
Sir, I am not able to share the screen. One second.
Yes, sir. We can see your screen, sir.
Okay. Okay, Professor. Shall I start? Professor, shall I start? Professor, my voice is audible. Shall I start?
Yes, sir. Yes, sir. Audible, sir.
Okay.
You can start now, sir.
Okay, thank you. Very good evening to all. To start with, I would like to thank Professor Palnichami for giving me this opportunity to share my little experience with respect to nitinol and wire additive manufacturing. So my title for today's presentation is an insight into the wire additive manufacturing of nitinol. Myself, Deepan Bharathikan. I currently work as an assistant professor in the Department of Mechanical Engineering, CEG campus, Anna University, Chennai. One second, I'm not able to share the screen. Yes, okay. One second. Professor, I'm not able to change the slide. I think it is very slow. Please give me a minute. I will check my network connectivity.
Yes, sir.
There is, sir.
Professor, your
There is,
screen is
sir.
visible now. Yes, sir.
பட் ஸ்லைடு சேஞ்ச் ஆக மாட்டேங்குது எனக்கு.
சேஞ்ச் பண்ணுங்க சார்.
அதான் சேஞ்ச் ஆகல. 1 செகண்ட் சார். I think now slide you are able to see now, sir. Professor?
Okay, okay, now okay, sir.
Okay. So sorry for the delay. So what I have planned for today's session is that first half I will try to discuss some fundamental concepts related to nitinol shape mineralized, and in the second half I will try to introduce what are the current trends and challenges with respect to wire arc additive manufacturing of nitinol, and I will end the session with by discussing some of the some of the future scopes of related to wire arc additive manufacturing of nitinol. So the session will be helpful for any individual who are in the initial stages of research and looking for some problems for their research work. I especially focused on nitinol shape memory and wire arc additive manufacturing. Again, I got stuck with this slide change. Okay. Sir, can you see my screen now?
Yes, sir. Your screen is visible, sir.
So I'm not putting in slideshow mode, sir, because in slideshow mode, I'm not able to change the slide.
No
Whether the
problem, sir. No
content is
problem, sir.
okay, okay. So as I said, in the first
Content is
half, I
also
will be
visible, sir. No problem.
okay. Thank you, sir. As I said, in the first half, I will be focusing mainly on the nitinol shape mineralize, and in the second half, I will be focusing on the wire arc additive manufacturing of nitinol shape mineralize. So to start with, shape mineralize belongs to a class of shape memory metals which have the capability to sense the change in atmosphere and respond to it in a predetermined manner. So some of the shape memory alloys were discovered in the early 1930s itself, and it was first observed in gold cadmium alloys and other copper-based alloys such as copper, zinc, aluminum, copper, aluminum, nickel are some of the other examples of the shape memory alloys. One of the recently developed shape memory alloy is nitinol. So basically, this nitinol stands for nickel, titanium, and novel ordnance laboratory. So actually, this nitinol, the scientists were able to find that nitinol is having this shape memory effect in an accidental manner. Actually, they were working in their lab, and at the same time, they were smoking. So they had a wire made up of nitinol, and they are playing with the wire by rolling it on their finger. So at the same time, they were smoking. So when the smoke ash fell on their finger, what happened is that the wire that was rolled on their finger got immediately straightened. So this was the turning point, and the scientists were able to realize that later this change in shape was mainly because of this alloy's capability of shape memory effect. So it was basically discovered in the early 1960 by these two scientists, William Bugler and Frederick Wang. Um, it has three unique properties, namely shape memory effect, superelasticity, and very good biocompatibility. And if it is processed properly, and it is possible to recover around 8% strain from nickel titanium shape memory. And in the currently in the commercial market, around 90% of the shape memory alloys are from this nickel titanium alloys only, along with the nickel titanium copper and nickel titanium niobium alloys. Basically, this nitinol exists in two phases. One is a high temperature stable phase, that is austenite. Another one is low temperature stable phase, martensite. The crystal structure of austenite and martensite is shown in the slide. Austenite exists in a simple cubic and martensite exists in monoclinic. In addition to these two stable phases, depending upon the processing that we are doing on the nitinol, there may be a possibility for the formation of R phase, and its crystal structure is trigonal. And generally, this R phase formation is not. It is not. If it is forming, it will have a negative effect on the properties of the nitinol. And with respect to nitinol, there are around 4 temperatures, starting from austenite start temperature, austenite finish temperature, similarly martensite start and martensite finish temperature. So, as the name suggests, austenite start temperature is the temperature at which this austenite phase starts to form. Similarly, austenite finish temperature is the temperature at which the austenite formation is complete. Same applies for martensite phase, martensite start, and martensite finish temperature. So these phase transformation temperature have a very huge impact on the overall property of the nitinol shape memorializer. So as it is seen in the picture, so we will try to understand the shape memory effect with the help of the picture shown in this slide. So you can see it in the first picture, that is in initial state, nitinol exists in twinned martensite and the temperature is around less than martensite finish temperature. And once we apply force to deform them, the spring gets deformed and get converted into deformed martensite. Now, if you are applying heat and if the temperature of the spring reaches more than austenite finish temperature, the spring will automatically get returned to its original state as it is shown in the third picture, which is highlighted in orange color. And again, if you cool this spring to temperature below martensite finish temperature, the material will exist in martensite space, but it doesn't change any shape. So this phenomenon of returning back to its original shape on the application of heat, that is what we call it as shape memory effect. And this is called one-way shape memory effect. And if it is processed, trained properly, it is also possible to train the nitinol to remember its shape both in martensite phase and austenite phase, but it involves a lot of training. That is a slightly tedious task. So what I do is that I will just share this video where you can get an understanding of this shape memory effect. So I'll be playing this video and you can see I'm having a wire in this video, and this wire I'll try to deform it and I will put it in the hot water. That austenite finish temperature of,
Excuse me.
sir.
The same, it is the same weekends.
Sorry, sir.
Actually, it is in the first slide only. Overview of the.
Oh, it's
Still,
not
we
changing,
could
sir.
see only one, only the first slide. Yeah.
Now you're able to see the slide change, sir.
No, sir, no.
Now, sir.
No, sir,
Now it
same.
is okay, sir.
Yes, sir. Now it is changing.
Okay, sorry, sir. I was not aware that it was not changing. So anyway, I will try to explain the shape memory effect through this video. So I will just play this video for a minute. Then I will give my understanding of this video.
Okay.
So as you can see it in the video, I have this nitinol wire whose diameter is around 1.2 mm. And I'm having two bowls containing water. The one which is on the left side is having hot water, and the one which is on the right side is having cold water. The nitinol austenite finish temperature, as prescribed by the supplier, is around 50 degrees Celsius. So what I do in this video is that I will try to deform the nitinol wire, and I will put it in the hot water. So when I put the nitinol wire in the hot water, you could see that the nitinol is automatically returned in its original shape. At the same time, you can see that you will be able to get a lot of actuation energy. So you can just see the video. I'm just deforming the wire and I'm rolling it on my finger. So now I'll put it in the hot water. So once I put it in the hot water, you could see immediately it is returning to its original shape, and also it will be thrown away from that hot water bowl. You can see from the video. So you could see that the wire is not visible now. Because of its good actuation energy, you can see that it has been thrown away to some location, and you can also see that the wire has returned to its original shape. So this phenomenon of returning to its original shape on the application of heat is what we call it as shape memory effect. So to understand it further, what I do is that again I will deform the wire and I will put it in the another bowl which is having cold water. And you can see from the video, when I put it in the cold water, you could see that there is no any shape changes happening. Why? Because the water temperature is less than the arsenide finish temperature. So the wire remains in the deformed state itself. So what we need to do is that we have to plan our application accordingly at reaching a particular temperature. If you're expecting an actuation, then accordingly we can use that wire. So this wire had an arsenide finish temperature of around 50 degrees Celsius. So when the wire reaches 50 degrees Celsius, automatically it returns to its original shape. At the same time, you can also get a lot of actuation energy. So this is what I was discussing in the initial slide related to shape memory effect. So I'll just skip to my next slide with this understanding of shape memory effect. Another advantage of this shape memory alloy is that we can also change the initial shape of the nitinol wire. So for that, I'll just share another video. Professor, can you just confirm whether the video you're able to see so that I can?
Yes, sir. Yes.
Oh, okay, thank you, Professor.
Yes.
So what I will try to share in this video is that initially this wire was having this V shape as the initial shape. Then we were able to train the nitinol wire and change the initial shape in some other form. You could see in from this video by proper heat treatment and proper maintenance at a particular temperature, soaking time, where you can achieve that also. So I'll just share this video. So you can see that once it reaches the temperature, the wire is returning to its original shape. You can see that on reaching the particular temperature, it has returned to its original shape. Now what we will be doing is that we will be taking this wire and sorry. So we were just checking whether this shape setting was possible or not. And what we did is that we had a small tongs to which we held this nitinol wire and we exposed it to our domestic gas for a long time. And after that, what we observed is that this shape became the initial state. I'll just share you again. We are just heating it for some time. So after some time, we tried to check what is the initial state, and you could see that now we have deformed the wire. When we just put it in the hot water, you could see that the new original shape has been reached and heating to the particular temperature. So the shape setting is also another advantage with respect to nitinol wire. So in case if you're having any wire and if you are interested to convert it in the form of a spring, that is also possible by using proper fixture. So this is about nitinol shape memory effect. Next important property what nitinol possesses is the super elasticity or pseudo elasticity. As you can see it in the slide, this super elasticity or pseudo elasticity is possible only at temperature more than arsenic finish temperature. So when you apply load, it gets deformed like a normal material. But on reaching point B, the material started to get converted into martensite phase. On further application of the load, the material transformation to fully martensite completes by on reaching point C, and on further application of load, it reaches the elastic limit and the yield point and further ultimate tensile point and then failure. So if you are removing the load after reaching C dash, that is below yield point, the material again will return back to its original shape by converting into arsenide start and arsenide finish on reaching point F and G respectively. So this phenomenon of stress-inducing martensite phase in the nitinol wire, at the same time, we are able to get maximum recoverable strain. That is what we call it as super elasticity. So this super elasticity is also helping nitinol to find application in variety of fields. So one of the important application is this braces that we use it in our teeth alignment. So this is another important property of nitinol. And because of these two important properties, on the whole, nitinol finds application in almost all the industries, starting from aerospace, automobile, robotics, fashion, and especially nitinol's penetration in the biomedical industries is on a very high level, and it is replacing the traditional materials such as stainless steel and titanium, which are currently used in biomedical applications. With respect to aerospace and automobile industries, it is mainly used for the purpose of actuation because it has a very good work density compared to other actuating mechanisms. And it has the capability to lift weight around 100 times of its original weight. For example, if it is having 1 kilogram weight, it can easily lift 100 kilogram weight. So because of this capability, in both aerospace and automobile applications, people are trying to use it and replace the conventional actuators with this nitinol shape immobilized so that the weight reduction will be achieved in the automobile and aerospace application. On the whole, it will also help us to address the fuel efficiency. At the same time, we can also concentrate on these sustainability aspects. Coming into the robotics, with respect to robotics, nitinol shape eminerals are mainly used for grippers, and also artificial muscles are also being tried with respect to nitinol shape eminerals. And main advantage is that it is having very good high degrees of freedom. And with respect to fashion industries, it is also possible to uh, combine this nitinol wire in our daily wear shirts. And suppose let us assume that when we are wearing shirt that is made up of nitinol wire, that is also it contains nitinol wire. So what happens on reaching a particular temperature, the nitinol will try to change the shape. As a result of that, the shape of the shirt also will get changed. So people are trying to use this for summer time, like when you are wearing shirt tightly, obviously it will not be comfortable for us because of the difficulty of the air to go into our body. So on reaching a particular temperature, the shirt will automatically will become loosened. So the air can freely flow and we can feel comfortable. So in that aspect also, people are trying to explore this nitinol shape memory for the fashion industries. And coming into the biomedical industries, mainly because of the two properties, that is shape memory effect and also super elasticity. And also the third important aspect of nitinol, that is very good biocompatibility. They are widely used in biomedical industries for the fabrication of implants and also medical accessories that are used to carry out surgeries and other small components. So I'd like to share some of the other videos which we have done with the help of our college BTech students. So they were trying to explore the usage of nitinol for the gripping purpose. And you could see in this video, there is a nitinol wire on the top, and they're trying to heat the wire with the help of a battery. And you can see they're holding it in their hand. So when they're switching on when they're switching on, you could see that the wire is getting heated up, and automatically the gripper is it is holding the cellophane tape that is held at the bottom. I'll just play this video so that we can understand in a better manner. So you can see it in the video, the students are pressing that switch. Once they press the switch, the temperature of the wire got increased, and it would have reached the austenite finish temperature. As a result of that, the wire got compressed, and that will be helping us to grip the component that we are interested to do. So this is one of the project that was done by our BTech students as part of their regular curriculum. And I'll show you another video where another batch of students tried to do a prototype where they're able to actuate the airplane wings. So you could see in this video, they're also using microprocessor as well as this battery for heating the wire. I'll just fast forward the wire. You can see this is very heavy, this metal plate. And you could see when they switch on the current, and automatically it will get lifted up. So this is a small prototype. They were trying to mimic that lifting of the wings in a small aeroplane. You could see they were able to lift this heavy weight with the help of these two wires present in the left side and right side. These are the wires present. Because of changing its shape to its original shape, that is compressed state is the original shape. Once it reaches a particular temperature, they were able to lift this wing. I'll just play it again so that you could see how fast it is getting lifted. So we can actually play with this actuation, how fast we need. All these things we can metallurgically play with the composition as well as the dimension of the wire we are using. Next, I will just show you another work that is done by one of our BTech students. So here they were using a fixture for converting the wire into a form of springs. Whatever they have done in the previous video, actually the students have purchased nitinol wire and they were able to convert it into spring, and they're able to set it as the initial shape. As we have seen it in the first couple of slides, they were able to change the initial shape like that. They were able to change the initial shape to spring by heating to a temperature of 750 degrees Celsius and maintaining it there for some time. So they were also studying the effect of chemical composition on the shape shifting, and they are currently working on that also. So what they found from their work is that what is the effect of current on the actuation. So we, depending upon the application, in some cases we may be needing rapid actuation. In some cases we may be requiring slow actuations. So what they found out from their initial preliminary data is that, as shown in the slide, when the current is on the higher side, that is 1220 milliamps, the actuation was very rapid. You can see that within 1.45 seconds, they were able to return to its original shape. But with respect to lesser current, that is around 850 to 700 milliamps, the actuation was slightly slower, and it was taking around 12.54 seconds. When they were supplying current of 600 milliamperes, the temperature was not rising to austenite finish temperature. As a result of that, the shape change was not happening. So what we could try to do in our future project is that we can just try to play with the amount of heat that we are giving, and accordingly we can control our actuation. So and also they studied the life cycle of this fabricated spring, and they found that after 20,000 cycles, the loss in length is around only 5.9 mm. So we could also explore this by altering the chemical composition and also studying the current that we are applying, so that the loss in length, if you see for 689, the loss in length is 0. So we are able to recover to complete shape. And for up to 10,000 cycles, the loss in length was around only 1.7 mm. And after 10,000, it got increased to 5.9. So because of some metallurgical changes that is happening, because of the continuous supply of heat, the students are observing slightly loss in length with respect to the shape memory effect. And they were also noticing some change in the phase transformation temperature. The initial phase transformation temperature, that is AF, was around 60 degrees Celsius. And for the helical spring, after the shape setting, it was shifted to 58 degrees Celsius, because you could see that nickel content initially it was around 55 and the titanium was 45. After that heat treatment for a certain time, the nickel content and the titanium content obviously will get changed, and it was around 56.88 and 42.05 for titanium for helical spring. And after 20,000 cycles, they're able to see that there is still changes in the chemical composition of the nickel and titanium. And as a result of that, the phase transformation temperature is also getting changed. So this is the actual challenge that what we have with respect to nitinol wire. That is actually, this was observed by one of our BTech students. So they proposed that we should be having some ideas to control this change in phase transformation temperature after using it for 20,000 cycles. So now coming into the biomedical applications, as I said in the beginning, nitinol is replacing the traditional biomedical materials such as stainless steel and titanium, mainly because of these good properties. Like its static life is around 50 million cycles, which will be more than enough for us to survive for our entire life. And also wear resistance is also reasonably good, and nitinol have a very high hardness. So the wear resistance capability can make the implant to survive around 50 to 20 years or even longer. And one more important thing with respect to nitinol shape umbrella is that it is not giving any carcinogenic or neurotoxic allergic activity on our human body when it is used as implant within our body. And another important aspect of nitinol is that if it is placed properly at the required locations, we can also change the shape of the nitinol after placing inside our body. So this will help the doctors to reduce the number of surgeries that we are actually doing, which will help us to recover quickly also. So the fourth point is one of the important advantage of nitinol. So in case if you are making stent and if you are placing inside our vessel, we know that the size of the veins or blood vessels are on very small scale. So what we can do is that we can compress the stent and we can place it on the required location, and it will automatically return to its original shape after reaching the body temperature. So like that, people are trying to explore in variety of human applications. Now people are also trying to place this in fallopian tubes of woman reproductive system, so that they were able to block the fallopian tubes, and the tissues also will start to grow around the implant that is placed in the fallopian tubes. These are all some of the works people are trying to explore using nitinol shape mineralize. This slide gives a comparison between the different materials that are used in biomedical applications based on its mechanical as well as uh, physical properties. As you can see it from the slide, the melting point of nitinol is on comparatively on the lower side compared with the traditional stainless steel and titanium Al6V4 alloy. And whereas the thermal expansion and the thermal conductivity is also slightly favorable, especially thermal expansion is very low, so it will be helpful for us to minimize the uneven expansion and contraction during heating and cooling. And elongation percentage, as it was said in the initial slide, if it is processed properly, it can we can recover around 8% of this time. That is very huge, and it is mainly used for the benefit of a lot of biomedical implants. And and also this is having very good MRI capability. So once it is placed inside our body, in case there is a need for us to go for scan, it is compatible with the MRI scan, so we can also get to know what is happening inside also. So that is another advantage with respect to using nitinol as bioimplants. So some of the biomedical applications I have listed in the next couple of slides to get an idea how they are used in biomedical applications. As I said in the previous slide, they are using it for the manufacture of stents and dental braces, as it is shown in this picture, mainly because of the superelasticity nature of the nitinol. Another important application is in orthopedic section, that is for the fabrication of staples. I'll just show you this video which was taken from YouTube where they will be using nitinol staples. As we all know, our bone fracture will get healed at a faster rate when the movement around that area is very less. So how this shape memory effect will help us to restrict the movement of the fractured bone, it is clearly demonstrated in this video. You could see this video. I'll just play this video for a while. So this is the shape of the staple. So what they will do is that they will just place it in the bone which has to be held together by drilling in the required location. So initially the nitinol staple will be in the converging shape. I'll just show you on the video. So this is the initial shape of the nitinol shape umbrella. What they do before inserting inside our body is that they will apply force and deform it to straight position. and they will keep it inside the body in straight position. So what happens on placing the human body is that on reaching our body temperature, that is, let us say 37 degrees Celsius, it will again try to return to its converging shape. As a result of that, we can comfortably hold the bones firmly and tightly, helping us in restricting the movement of the bones and aiding us for quicker healing of the bones. I'll just show you. Sorry, I'll just play that. So this is the initial shape. Deforming it before putting it in our body. Once they place it in our body, you could see that automatically on reaching the temperature, it will try to convert into its original shape. So on the whole, it will be helping us to hold it tightly and helping us to heal the fracture at the faster rate. So these are all some of the other important or innovative applications where people are exploring this nitinol shape mineralize for biomedical applications. So another applications, this we might have seen. This is also I have taken from an YouTube video. We could see that they are these spectacles that we use for our day-to-day purpose. They will just deform it by applying force, but on reaching the room temperature, it will again come back to its original shape. So no need to worry about the frame getting damaged, since once it is getting temperature is risen to the austenite finish temperature, it will come back to its original shape. I'll just show you this video and I'll also fast forward. You can see it from the video. They are just bending it to whatever shape they want. So another important thing with respect to this nitinol is that, as I said in the beginning, it has two phases, namely martensite and austenite. Comparatively, here martensite will be on the softer side, and austenite will be slightly on the harder side. So martensite is a stable phase at low temperature. That's why they are cooling it with the help of some cryogenic fluids, and they are deforming it to required shape. And once they keep it in the normal room, and with respect to change in temperature, gradually you could see that the specs is getting returning to its original shape. We'll just fast forward. We could see that the specs has come to its original shape as it was present in the initial stage before deform. This is another important application of nickel titanium shape mineralize. So on the whole, because of shape memory effect and super elasticity, nitinol is fetching a lot of applications, mainly wherever we need actuation and our biomedical applications. You can explore in a variety of locations like hip implant, and also the stiffness of the stiffness of our bone is almost similar to this nitinol shape minerali, which help us to protect the bone getting damaged by acting as a stress shielding. So in case if the stiffness is different, then the load may get acted on the implant and more, and our natural bone may get weaker. So that is also another advantage with respect to nitinol shape mineralize. So both the stiffness of bone and nitinol shape mineralize are almost same. So it will help us to protect the bone to get damaged. Another advantage is that it is also having very good kink resistance. So that's why they are using it for making a lot of medical tubes, accessories that are placed inside our human body. So this is what I was planning to discuss in the first half of the session to understand the importance of nitinol shape mineralize based on its properties. And with respect to properties, I was sharing what are the options available for us to explore in various domains. So now what I do is that I will shift my focus towards 3D printing. What are the current trends with respect to 3D printing of nitinol shape mineralize? What are the challenges, and what are the new novel methods people have developed that can be explored in the coming work, so that we can fine tune the properties of nitinol shape mineralize. Professor, whether my voice is audible?
Yes, sir.
Okay, Professor. So now I'll shift my focus to 3D printing. So as we all know, this 3D printing has become a revolutionary technique. I think a lot of peoples from various companies as well as colleges might have explored, discussed the advantages and what are the good things that we have with respect to 3D printing. So before going to wire additive manufacturing of Nitinal, I would like to just refresh you with this 3D printing. So there are actually 7 classifications of 3D printing, starting from matte photopolymerization, material jetting, binder jetting, material extrusion, direct energy deposition, powder bed fusion, and sheet lamination. And with respect to this original shape and realize, a lot of works has been done, and it is reported in the literature, focused mainly on direct energy deposition and powder bed fusion. So to get understand the importance of 3D printing, I just wanted to highlight some of the real-time case studies which is helping humans community in a broader significant manner by taking this SJD Barcelona's Children's Hospital case study. So as uh, as we all know, carrying this surgery on a human body is a very challenging task. And if it is done by an inexperienced doctor, there is the chances for him to make errors. And because of the error, there is a possibility for us to have a negative impact on the life of the patient, which is under surgery or something like. So, how people are using this 3D printing is that. So people are actually using 3D printing to print the actual physique of the patient and practicing it using the 3D printer model. And they are analyzing what should be the way the operation has to be done so that we could complete the operation at a faster time. At the same time, there is less risk to the life of the patients. So this case study was taken from online resources only. So this was used for addressing this tumor that was present in children, especially in this complicated region of our front face. So you could see from the picture if a small child is having a tumor in this location, and if the doctor has to operate in that location, the complexity of that structure as well as the eyes, nose, all the nerves endings, if it is not properly considered before operation, that may have a negative impact on the life of the child. So what they did in this Barcelona's Children's Hospital is that they actually scanned the child's skull, and they're able to print a skull with the presence of that tumor, and they are able to analyze that skull with the presence of printed tumor, and they were able to understand how this operation has to be done so that they can complete the operation at a lesser time, and there is no negative effect on the other side of the other parts of the face. So they were able to do with the help of this fusion deposition modeling, and they were able to successfully remove the tumors also, and the child is also performing normally after the surgery. So this is one of the groundbreaking significant contribution of 3D printing in our real-time applications, which not only saves the cost but also can help us to save the life of a lot of humans. It also can help us to save a lot of human lives. So another example, I think we might be aware about this uh, news, which was seen in the year, I think 2024 or 23, I'm not sure. And it was also, especially in civil industry also, people are trying to explore this 3D printing by larger amount. And L&T were able to build this post office, which is located in Bangalore, for about only 2.6 million rupees. And it was around 40% lower than the traditional way of constructing this post office. So they were able to construct it with lesser time compared to a traditional way of doing this construction. So from these two case studies, we could understand this how this 3D printing is helping us to revolutionize our human life, not only with respect to improving our sophistication, but also helping us to save the time and life. So now we'll come back to this nitinol shape umbrella and what are the challenges with respect to traditional manufacturing of nitinol and why there is a need for us to go for 3D printing of nitinol. So nitinol, as discussed in beginning slides, nitinol is having very high hardness. So if a material is having very high hardness, we know it will be very difficult for us to machine, and the proper identification of tool is an issue. So tool wear may be an issue. So that is having a negative impact on the converting the nitinol into required shape as well as complex shapes. Traditionally, they are using these they are using these traditional manufacturing processes like casting, machining, powder metallurgy, and to some extent welding, wherever there is a need for us to go for complicated shapes. So the general issues that they have with respect to this nitinol, in addition to this higher tool wear, the efficiency of the process is also on the lower side, and the time taken for the complex fabrication of the particular component is also on the higher side, and then dimensional accuracy also on the on the lower side, and nitinol is slightly sensitive to higher temperature. For example, if you are taking the nitinol to higher temperature, there may be negative impact on the chemical composition, and it will alter the phase transformation temperature, which in turn affect the shape memory effect and superelasticity. So the process by which we are fabricating the implant or any other actuation system should be carefully chosen so that there is less changes with respect to the chemical composition. If there is no need to worry about the shape memory effect or phase transformation temperature, then the traditional method may be more than enough for us to get the required shape. For example, is also having very good corrosion resistance. So if you're able to get reasonable corrosion resistance by traditional manufacturing process, and if you are not worried about shape memory effect, then we can stick with the traditional manufacturing process because of the lesser cost involved with respect to it. So with respect to mass production, conventional manufacturing will be a go-to option. Whereas in case of complex shapes, fabrication of complex shapes, and the volume of requirement is also on the lower side, then obviously 3D printing will be on the one of the preferred options than the traditional method. So wherever there is a need for us to go for complicated shapes and there is less volume requirement, 3D printing will be economically also helpful and beneficial. So till date, with respect to nitinol, 3D printing of nitinol, in the literatures, there are two categories of additive manufacturing has been explored. One is powder-based nitinol. Another one is direct energy deposition of deposition process. So with respect to powder bed fusion, it has certain advantages and certain disadvantages. So one of the most used powder-based processes, laser-bound powder bed fusion, as well as electron-based melting, laser-based melting. So these are all some of the processes that are generally used for fabricating nitinol shape alloys. The challenge is generally it is what it is reported in the literature is that porosity is one of the major problem with respect to powder bed based processes, and process efficiency is on the lower side. But the advantage with respect to powder bed fusion is that it is having a very good surface finish, and also it is having very good dimensional accuracy. So this is another advantageous side. Whereas with respect to direct energy deposition, in direct energy deposition, we'll be using wire additive manufacturing, which is nothing but we will just see the working principle of wire additive manufacturing in the next slide. But sticking to the advantages and disadvantages, VAM of nitinol is on the lower side because of the initial investment that is associated with respect to the power source, and efficiency also on the higher side. But the problem with respect to this wire additive manufacturing is it results in poor surface finish, and dimensional accuracy also is on the lower side. So we have to choose the process according to our requirement. In case if you are focusing on the good surface finish, then the powder bed fusion may be go to option. In case if you are okay for going for finishing operations, then wire additive manufacturing may be handy since the overall cost associated with respect to this process is on lower side. At the same time, the time taken to complete the process is on the lower side. What I have found from the literature is that with respect to powder, the cost is always on the higher side. For example, with respect to titanium AL6V4, per kg of powder is around $300, whereas with respect to same material, wire is only around $125 per kilogram. You could see that it is almost double when you're using it in the form of powder. And the handling of the powder is also a challenge because we need to remove the excess powder and it has to be recycled properly. And with respect to stainless steel also, the wire cost is around $15 per kilogram, whereas the powder cost is around $45 per kilogram. So it is almost 3 times higher than the wire. So economic aspects is one of the main priority. Then I think the wire additive manufacturing could be explored with respect to retinal shape embryologizer. So basically, this wire and additive manufacturing is similar to it is nothing but the welding processes only. So we will be using welding power source to generate arc, and we will be using a wire. That wire will be melted with the help of arc, and it will be deposited layer by layer as per the digital design that we have made it in our software, whatever software we are using. So I'll just play this video, which we have done with in collaboration with one company, but it was not done with linear shape membrane, but it was done with steel-based wire. So I'll just play this video to get an understanding of this wire additive manufacturing. You can see that the wire is getting melted and it is getting built over the already built layers. So this is a CMT-based process, and you could see that the time taken to build is also on the lower side. And you can just use our traditional MIG welding setup also to perform the same type of layer by layer building. In case if you are focusing on complicated shapes, then we have to get the assistance of a robotic setup. So, and we have to plan our tool path and slicing and all, which has to be taken care of so that we get the complicated shape. So this is where this was done as part of our BTech student project, where they explored the wire additive manufacturing of steel, and they are just trying to understand the metallurgical aspect. So they are not going for complicated shapes. So they're just trying to build layer by layer, and they are trying to explore the metallurgical changes as well as the mechanical properties. So this is what we'll be doing with respect to wire additive manufacturing. So with respect to the literatures, as you can see it in this slide, the number of papers that were published with respect to additive manufacturing on the whole, including all the 7 different categories, you could see that laser-based powder bed fusion is on the higher side, and other processes are not explored that much. And you could see that wire additive manufacturing is also on the lower side. So if any researcher are in the beginning stages of research, instead of focusing on laser powder bed fusion, there are scopes for us to explore other type of process which is having metal compatibility, and this for all the metals, not specific to nitinol. And this slide gives an idea about the number of papers that is published only in VAM. And you could see that from 2016, gradually the number of papers is getting increased, and it is around 122 in the 2023. And this was a paper published in 2024, and that's why they have taken data up to only 2024. And you could see that only 122 papers are published focusing on the VAM. And additive manufacturing of nitinol in specific, you could see the number of articles is very less. Around 2022, it was only around 70 papers. As well as the help of the filler wire you're using. So with respect to wire coating manufacturing, traditionally people are using three power sources. One is MIG, that is metal inert gas. Another one is junction inert gas welding. Another one is plasma arc welding. Comparatively, plasma arc welding has a higher power density. As we all know, when the power density of the power source is on the higher side, it will have very good positive effect on the properties of the layer that is getting built. So we need to have a clear understanding of the power source before choosing the type of before building the layer. We need to have a clear idea of these three power sources, and according to our need, we have to choose. If you take this MIG welding power source, it may be having a good deposition rate, like around 2 to 3 kilogram per hour. Whereas laser based powder bed fusion, it is having only around 150 to 200 grams per hour. You could see how big the difference is. In this wire and country manufacturing, the deposition is around 2 to 3 kilogram per hour. Whereas in case of powder bed fusion, it is only around 150 to 200 grams per hour. And with respect to electron beam welding, it is around 600 to 800 grams. Still, it is lesser than wire and country manufacturing. So if you are interested in depositing at a faster rate, then wire and country manufacturing should be the one of the preferred processes. Another advancements with respect to this wire country manufacturing is that constantly a lot of advancements have been done with respect to the power source to minimize the overall heat input so that the thermal damages are minimized. So like how we do with respect to welding, people have explored this old metal transfer arc welding for exploring the wire country manufacturing of nitinol shape mineralize. Most of the works done in nitinol shape mineralize is done with respect to CMT, cold metal transfer arc welding, where we have a special type of setup to retract the wire front and back, which will help us to reduce the heat input, and also it also helps us to minimize the spatter. So this is also people are exploring to larger extent with respect to nitinol shape mineralite. Another advancements what we could some of the people explore with respect to nitinol is this twin wire directed energy deposition. This was done with respect to plasma arc torch. And you could see it in the right side. There are two wires. One is titanium, another one is nickel. So according to our requirement, we can control the feed rate of this nitinol titanium wire and nickel wire so that we can control the composition also. So composition plays an important role with respect to all the properties of nitinol shape mineralizer. So this table gives a comparison of deposition rate with respect to the different power source that I have mentioned in the previous slides. Please, 1 second, I'll just have my water. Okay, thank you. Professor, is it audible? My voice is audible?
Yes, sir. Yes, sir. Audible, sir.
Okay, thank you. So this table, you could see that comparatively, this twin arc, that is a tandem, it is having around 6 to 8 kilogram per hour, whereas MIG is having around 3 to 4. CMT, since we are focusing on minimizing the spatter and the heat input, it is around 2 to 3 kilogram per hour. TIG, as we all know, TIG is one of the cleanest arc welding process. So the deposition is on the lower side, but the quality may be on the higher side. If the deposition rate is not a concern, people can prefer TIG-based wire cutting manufacturing for building the shapes for nitinol shape mineralized. It is around only 1 to 2 kilograms per hour. Whereas in case of plasma arc welding, it is around 2 to 4 kilograms per hour. So according to our requirement, people have explored CMT, and people have started to use this twin arc wire also with respect to nitinol shape mineralizer. These are all some of the materials that I have gone through from the literatures I have taken. These are the shapes people are able to print using this wire cutting manufacturing, and using materials like aluminum, titanium. Shapes they are able to get like this landing gear, food bridge, pressure vessel, and mainly they are able to do with respect to aluminum, steel, magnesium, titanium. Most of the works is mainly focused on this steel and titanium. So with respect to nitinol, the number of papers is very minimum. So in case if anyone is planning to start a research, I think they could explore this area for good paper publications. So in the process of wire cutting manufacturing, in the fine tuning of this wire cutting manufacturing, we have to give importance to the process that we are going to use, because obviously it is having control on the deposition rate, as mentioned in the previous slide. And we have to give importance to the process parameters like current, that is overall heat input, which is controlled by the current voltage, as well as wire feed rate, as well as the speed, welding speed. So these has to be fine tuned properly so that we can control the metallurgical changes in a favorable manner. And another thing is that we have to prefer correct shielding gas. In some people, some works people are fully preferring argon-based shielding gases, and in some works people are able to combine argon with oxygen to stabilize the arc. So there are scopes for us to explore the different shielding gas combination, which will help in fine-tuning the properties of the wall that we are building. And wire selection also, it is very important. The size of the wire, that is diameter of the wire that we are using, and purity of the wire, as well as the other aspects of the wire has to be considered. What is the initial condition, whether it is annealed or solutionized, all these things will come into the picture when you're trying to control the quality of wire cutting manufacturing. So coming into the challenges, specifically with respect to the nitinol shape member alloy, small change in the chemical composition will have a very large negative effect on the phase transformation temperature. So if you remember in the beginning slides, I told you that the shape memory effect mainly depends upon the 4 transformation temperature, that is austenite start, austenite finish, martensite start, and martensite finish. So if during wire cutting manufacturing, if the heat input is not selected properly, it may change the chemical composition, and we may not get the wall as per our required austenite finish temperature, because on reaching austenite finish temperature only, the wall will return to its original shape. So as it is mentioned in this slide, you can see that the martensite start temperature, when the chemical composition, that is nickel fraction, is around 48%, it is around 340 degrees Celsius, sorry, 340 Kelvin. Small change in the nickel content as we move it in the right direction, you could see that on reaching around 50, 51, something like that, when the nickel content is around 51%, you could see that martensite start temperature is drastically reduced to 50. So for around 3% change in nickel content, the martensite start temperature is changing from 350 to 50, around 300 Kelvin difference. So this is one of the major challenge that we may face whenever we are doing welding and also wire cutting manufacturing, because we are exposing the nitinol to higher temperature. So obviously this temperature will have a negative impact on the chemical composition, and in turn it will have an effect on the shift in the martensite start and martensite finish, as well as austenite start and austenite finish. And in some cases, as I said in the first slide, some cases there we may be also noticing a phase called R phase, which may shift the martensite start temperature. So that is also another challenge with respect to wire cutting manufacturing. So if the phase transformation temperature is getting affected, obviously the shape memory effect also will be getting affected. So what we need to do in case we are planning to control the shape memory effect is that we need to fine tune the grain size, and we have to minimize this R phase transformation, and we need to do the wire cutting manufacturing in such a way that there is no defects like pores, cracks, and any other inclusions because of improper shielding during wire cutting manufacturing. And we need to make sure that the nickel content is not getting change. Okay. And then residual stress, obviously, because of the uneven heating and cooling, it will be resulting in residual stress. So that also has to be minimized in case if you are focusing on shape memory effect. But if the shape memory effect is not required, only we are using it for the good corrosion resistance and good mechanical properties, then it will be very easy for us to print this nitinol shape memory alloys. Still, we need to focus on the parameters as well as process, but shape memory effect is the major challenge. So other challenges is that it mainly results in this brittle intermetallic phases like NiTA2, Na4Ta3, because of the non-uniform heating and cooling and various reactions that is happening during the cooling process. So if it is not controlled properly, you may get these brittle intermetallic phases, which in turn will have a negative impact on the mechanical properties as well as corrosion properties, and also this nickel content will get slightly altered. As a result of that, phase transformation will get affected, then shape memory effect will be getting compromised. So we may be expecting the material to change the shape on reaching 50 degrees Celsius, but it may get changed after reaching 75 degrees Celsius. So that is the challenge that we are having, especially with respect to wire cutting manufacturing. So we need to have an eye on this precipitate unwanted brittle intermetallic phases that we are that is getting formed. We should fine tune the parameters as well as process such that the morphology of all these phases are controlled. So with respect to the recent advancements, if anyone is planning to start this wire cutting manufacture of retinol, people can explore recent advancements with respect to this MIG-based power sources such as spin arc-based torch. I think I couldn't see any literature related to this, especially focusing on retinol, which is having a lot of advantages compared to the traditional MIG-based power sources. And twin arc, a couple of papers are present with respect to retinol, but still a lot of work could be done with respect to twin arc of nickel titanium shape umbrella, and then double pulse, which is an advancements with respect to single pulse, where we'll be having high frequency and low frequency waves pulses superimposed over one another. Another one is interpass cooling and interpass cold running. These are all some of the advancements that are explored in other materials, which we could use it for our research. I'll just show you with the picture in the coming slides. This is an forced gas cooling, which is helpful for us to control the interpass or interlayer temperature. So when you're building the first layer, what should be the when the next layer has to be built? That is the question mark. So we need to identify at what interlayer temperature the next layer has to be built. If we are doing it immediately, the molten metal get disturbed, the flow of the molten metal will get affected. If you are cooling it, if you're allowing it for a long time to cool, and if you're passing the next layer, the adhesion between the two consecutive layers may get compromised. So we need to find what should be the correct interlayer temperature such that the adhesion between each layers are on the higher side. So you can see that this is one option. What people could explore is that they can use a separate gas to cool the layer, monitor the temperature, and then we can build the next layer. So this is this was explored in some other materials. This can be explored in retinol, and we can combine this wire cutting manufacturing and retinol, so to get the benefit of rolling. So we know that rolling process will help us to fine tune the properties by altering the grain orientation. So this could be another option by combining rolling along with wire cutting manufacturing. So you could make the use the rollers to pass over the first layer, and second layer can be built again. You can use roller. So that also, since we are combining two processes, the challenges will be also on the higher side, because we have to fine tune both roller parameters as well as the MIG torch in case if you are using. As I said in the first previous slide, double pulse. This is a schematic of double pulse. Double pulse, that is a recent advancements with respect to MIG-based VAM, where we'll be using thermal pulse phase as well as thermal base phase. Because of the change in thermal pulse phase and thermal base phase with respect to microsecond variation, we'll be having stirring effect in the molten pool. As a result of that, it will help us to minimize porosity, and also it will help us to minimize crack formation, and also it will help us to fragment the dendrites, leading to fine grains. So this was well established in a lot of welding processes, welding of other materials. We have also some personal experience of exploring this double pulse MIG welding based power sources for joining different materials. With respect to VAM, I was able to see just only a couple of papers, so not also not explored with respect to nitinol. So that is an option for us to explore with respect to nitinol shape MRI, and we can get the benefit of double pulse MIG based power systems. Another one is spin arc based system, where the pillar wire will be rotating at a constant speed in a constant diameter. So this will also help us to build the layer at a faster rate. Molten metal, the deposition rate also will be on the higher side. And through literature, I found that people are using it for joining two materials. But with respect to wire cutting manufacturing, there are limited literatures using this spin arc based power torch, spin arc based MIG power source. So these are all some of the advancements that could be explored with respect to wire cut manufacture of nitinol. So to the major takeaways, what I would like to conclude this, how I'd like to conclude this presentation is that nitinol, mainly because of its unique properties, that is shape memory effect, super elasticity, and very good biocompatibility, it is penetrating the biomedical industries, not only in the biomedical industries, in aerospace, automobile, in all these industries, they're having a lot of opportunities to get use it for various applications, especially for actuation systems, if you are interested in weight reduction and controlling the chemical composition. Obviously, when it is exposed to temperature, it will have a negative effect on the chemical composition. It may get altered. It will get altered. As a result of that, the shape memory effect may get compromised. So we need to focus how to control the variation in the chemical composition by fine-tuning the parameters as well as correct process parameters. So it is also in the VAM is also in the initial stages of research, especially with respect to nitinol. So people could explore this material for their research work. But one problem with respect to nitinol, what we face is that the cost of the nitinol is on the higher side. So 1 kilogram of nitinol is itself around 1 lakh rupees. So unless if you get funding from a central funded institution or from our academic institution, then 1 lakh from our pocket may be a challenging task. So if we are getting fund, I think this could be one of the interesting material to work on, and a lot of challenges are present with respect to controlling the chemical composition and the formation of brittle metallic bases. If it is addressed properly, I think we can also expand the usage of nitinol in other application also. So this is what I was I have planned to deliver. Hope you are able to get some useful information through this presentation. So I will hand over the session to Professor Palnichami. And if any queries, please post it in the chat box so that if I know, I'll try to address some of the queries. Thank you very much for your patient hearing.
Participants, do you have any questions for clarification? Please ask Dr. Bharati Kannan, sir.
Very good evening, sir.
Good evening,
Hello.
Professor.
First of all, I would like to thank you on behalf of participants.
Yes,
Your
Professor,
session
please tell.
was very interesting and very informative.
Yes, Professor, because of the nature of the material, hope it was useful.
Yes, I have only one doubt. 1 lakh rupees, we can't do any research on that material.
Yes, Professor.
From last, you have shown that one of the slide, microstructure, that hexagonal structure you have shown, I think.
Okay, Professor.
Is there any specific property?
Which one, Professor? Which slide?
I think from last 4th or 5th slide, from last 4th or 5th, I think.
No, Professor, this was just shown to understand the benefits of hybrid VAM, where here we are using VAM followed by rolling. So we know rolling has certain benefits. When it is done, we can alter the orientation of the grains also, and the grains can be controlled. So once the grains are controlled, obviously the properties also will be on the advantageous side. That is what I was trying to say. So you could see the grains and the defect presence. So just I wanted to highlight rolling benefits also can be used to used in this setup. That is what I was trying to say, Professor.
Okay, sir. Okay, so thank you so much for your presentation. Really, it was very good, as well as that very informative. Especially, I enjoyed where that application, biomedical application. Especially, you told that stunt that
yes,
the blood
Professor.
vessels you have to, due to the body temperature, that material will behave. It's really
Yes,
amazing. I wondered actually that applications.
Yes, Professor.
Thank you so much, Professor. Thank you so much for your presentation. On behalf of participant, I would like to say thank you once again.
Thank you, Professor. Thank you for your nice words.
Thank you, sir. Thank you.
Sir, good evening, sir. This is Raghunathan from Mohan Babu University.
Yes, Professor.
Sir, I have a doubt. Like after making blank using this VAM technique, right? So in which orientation we have to extract testing specimens, sir? I have doubt in that because every layer by layer we are building, right?
Yes, Professor. Correct. You are asking correct question. I didn't address that challenge. One of the
Sir.
other challenge with respect to wire cutting manufacturing is that it is resulting in anisotropy. So in each direction, the property will be obviously different. So we need to fine tune the parameters as well as process. So which is resulting in lesser deviation. That is what we have to focus. So you have to measure in horizontal direction, vertical direction, and inclined direction, whatever direction you are interested to measure. And if it is obviously it will result in anisotropy. So we have to do in such a way that the changes are minimized as much as possible.
Okay.
So that is also people are trying to explore with respect to advancements of that. This is not only with respect to nitinol shape mineralized. This is for other materials also. This is the characteristics of this wire cutting manufacturing.
Actually, irrespective of material, we have to go for different orientation in extracting of specimens, right?
Yes, Professor. You can check it in any paper. They would have mentioned the sample in what manner they have cut it. So they would have cut it in horizontal direction. If you are measuring tensile strength, you would have cut in the horizontal, vertical, and inclined manner also. So they will do it in all the three direction, and they will give an idea of how is the properties changing with respect to direction. So you have to go for all direction.
Sir, one more clarification, sir. Actually, I am a welding person. I am planning to enter into this VAM technique. That's why I am asking you. This one, again, this is kind of all weld metal. Okay, na? After making blank, this is a kind of all weld metal. So any specific ASTM standard is there to go for testing, all other testing?
Yes, Professor. Sir, it is a well-established process like welding. For this also, they have standard that is given that should be followed for checking your properties as well as the procedures that need to be followed. So, if possible, I'll share the published papers where they have mentioned all these standards, so that you could also use it for your experimental work as well as analysis. Sir. I will share the paper, sir. Whatever I think I have given references during my slide in each slide. That reference itself, you could see the standard that they're following. If possible, I'll share through Professor Palnichami. I think sir will be able to communicate to all of you.
Nice, sir.
You can find it from the science director, Professor.
Okay, sir. Okay. Well, informative, as before Professor said, it is really eye-opening presentation, sir, for the beginners. Thank you. Sir. Thank you.
Professor, is there any other questions? If no questions, I'll.
Participants, do you have any questions? Or otherwise, close the session. Sir, shall we close the session, sir?
Yeah, before closing, I would like to again thank Professor Palnichami for giving me this opportunity to share my little experience with respect to nitinol shape embryolite. I'm also trying to explore this material, and especially with respect to biomedical applications. So if there are any more clarifications needed, I would be happy to respond if I know, or otherwise I'll refer it and I'll clarify it through mail. I will also share my mail ID. You could also just search my name, Deepan Bardikaran. You could get my mail ID. Thanks once again, Professor Palnichami and their entire college for organizing this beautiful ATAL workshop. I think participants are getting enlightened in various aspects of additive manufacturing. Thank you very much, Professor.
Thank you, Professor. Thank you very much.
Thank you, Professor.
Gopi, sir.
Sir, shall we close the session, sir? Okay. So thank you, sir. On behalf of organizing team, I sincerely thank Dr. Deepan Bardikaran, Assistant Professor, Anna University, Chennai, for delivering and enlightening and engaging the session on an insight into wire arc additive manufacturing of nickel titanium NOL Your valuable inputs have added great value to this program, and we truly appreciate your kind presentation with us today. Thank you, sir. Thank you, participants. Please wait for next session. Thank you, sir.
Professor, you can close the session now. Thank you.
Thank you, Professor.
Thank you. Thanks. Participants, please wait. The next session is about to start. Participants, please wait online. The next session is about to start. Manohar.
Good evening, all. Can we start?
Hello.
Good evening, Professor.
Sir, good evening, sir.
Can we start the session, sir?
Okay, sir. First of all, I introduce ourselves. The next section, we hand over to Mr. Manogaran Duraisamy. The title, Empowering Industry 4.0 with Generative AI. We warmly welcome Mr. Manogaran Duraisamy, an AI and Innovation Lead at GCC, Chennai. With over 25 years of IT industry experience, a visionary generative AI architect, he has designed and deployed enterprise-level solutions in AI, big data, and blockchain. His career spans leadership roles in DXC technology, HCL, and ALOX. He is specialist in AI-driven enterprise applications, computer vision, and data engineering. He is certified in MuleSoft and Apache Spark and has built blockchain applications and a smart contract. With his vast experience across healthcare, banking, and manufacturing, Mr. Manogaran is a recognized leader in AI-driven innovation and digital transformation. This session is handed over to Mr. Manogaran Duraisamy, sir. Thank you, sir.
Thanks for the introduction. Screen. Hope everybody can see me. It's, yeah, the title is Empowering Industry 4.0 with Generative AI. And we are going to focus especially on the smart manufacturing and predictive maintenance because AI has wide usage. But today's focus is only on the smart manufacturing and maintenance side of it. Before that, a little bit of introduction about me. I did my mechanical engineering in ACCT Karaikudi. I have more than 2 decades of IT experience, specializing in AI, big data analytics, blockchain, APIs, IoTs, all because of we got to always keep in touch with the technology to be current in the market. Not only that, I'm very much interested in learning. So I always learn new things and keep abreast in the market. Okay, just an overview on Industry 4.0. What is Industry 4.0? 4.0 is the integration of the digital technologies with the manufacturing world, right? It merges the physical production with the digital technologies for the smarter and autonomous manufacturing. Okay, let's look into the evaluation of the Industry 4.0, right? Industry 1.0 is about the discovery of the steam engine or the invention of the steam engine, where the steam power came and then the power looms came, which are used the power looms, right? And the Industry 2.0 is all about electricity and mass production of automobiles prevailed. And then Industry 3.0, which happened in the 20th century, right, where the computers got introduced and then the automation got introduced. And right now we are in the 21st century and Industry 4.0, where the digitalization meets the manufacturing, right? So within the digitalization, right, what I mean is IoT technology, AI, big data, and several other things. Right? Okay, so what are the key technologies that is driving Industry 4.0, right? The key technologies are IoT, or more specifically, industrial IoT, right? IoT is Internet of Things, where we have sensors connected to the network and constantly streams the data from the machines, from the cameras into the network or into the servers. From there, we can get insights out of the data. Okay. AI and machine learning, artificial intelligence and machine learning, right? They go through the data, whichever the IoT sensors produces, and then it provides big data and cloud. What is big data, right? The traditional system or traditional database management system has a limitation of handling huge volume of data. That's been addressed by big data. So when you have millions of sensors connected and millions large streams of data coming in, all those data needs to be handled by the big data platform and cloud, right? Cloud and platform. And on the hardware side, right? And now they are called cobots, which can collaborate with human beings, and digital twins, right? Which is nothing but the virtual replica for simulation, monitoring, testing, right? More specifically, answering scenarios. And also the printing, right? Manufacturing is not about mass production, it's also about personalization. Using the items which is possible, right? We can do personalization there, and within personalization, we can do mass production. That's where 3D printing came into the picture. So these are all the technologies, right? Digital technologies help. What is generative AI? Right? We heard about AI, artificial intelligence, and machine learning, which is traditionally like used for a classification or forecasting problems, right? Generative AI, right? It generates content. It creates contents. How do we create it? How do it does? It does based on the data it has been trained on, and it's trained on huge volume of data, right? The volume of the data it's been trained on is web scale. Whatever the data available on the internet, right? The models get trained, and now, right, they've created the model out of it, and it's capable of handling any questions. Yeah, and it just original content. There are various types of AI, like GANs, generative adversarial networks, variational autoencoders, transformer-based large language models. We are specifically going into the transformer-based LLMs. So what is an LLM? LLM is a large language model, right? Which is designed to process and generate human-like text, so that it's trained on vast amount of text data to understand the language patterns, right? So that's why, right? It's trained on billions of parameters, right? If we ask questions on any topics, it's able to answer because it's on it. Not only that, right? There are always new data coming in, and how it is able to answer, right? Not only the previous data, whatever it's trained on, it has also the capability to do a web search or do a search on the custom data, augment the data, and give the. So how do they learn? They learn on the predefined data set. We have either books or articles or websites or all the data sets available in the internet, right? Once we have the base model, right, we can fine tune it to a particular use case. For example, reading medical images, we can fine tune the base model to read medical images, or to answer any query on related to law. We can do that, which means we need to fine tune your base model with a specific domain specific data, and then we can generate output of it. In manufacturing, the font is see. We try to increase the font size. So within manufacturing, we can use for product design, right? Automatically, it can generate optimized part design based on the constraint, right? If you want to do a POC, or if you want to create a part and you want to do a POC, right? You can use generative AI to generate multiple alternative design with a given same people to do with the human effort alone, right? And already in the market, like tools like Autodesk Fusion, Siemens, right? They've already integrated generative AI into their tool. Process optimization, you have
Sir, Manohar
process
sir.
routing sheet of your job. Give it to the generative AI.
Hello, sir.
Sorry. Any questions? Yeah.
Sir, your voice is not clear, sir.
Any questions?
Your voice is not clear, sir.
Voice is not clear. Voice is breaking, sir. Sir, my voice is breaking, or sir, is it any better now, or still it's not clear? It's not that one person can answer. Anybody can answer if there are any issues, right? Can you hear me first?
Yes, sir. Yes, sir. Audible, but not clear, sir.
Can you hear me?
Yes, sir. Yes, sir.
Oh, looks like
Participants, please wait. I think sir have some network issue. We will join in a few minutes.
My side. Anybody want to hear me?
Sir, still not clear.
Still not clear. Okay. Just one moment. Please. Is it any better now?
Now okay, sir.
Okay, sir. Thank you, sir. Sorry for the mess up. Okay, let me see.
So please share your screen, sir.
Yeah, I'm sorry. Sure. Okay, so the key applications of generative AI in manufacturing, we have covered the product design and process optimization, where we can feed our routing sheets, right? Routing sheets are the standard operating procedure for any jobs, right? We can feed into generative AI and get a recommendation on it, right? For example, you can get changes to reduce the cycle time on a CNC machine operation, right? And predictive maintenance, right? It can use to analyze the maintenance logs, error logs, IoT sensor data, and it predicts the equipment failure, and that based on the recommendation, right, we can take actionable items or take action items and work upon it, right? And generative AI in manufacturing can be used on the to automate many of the process, right, which right now RPA is doing. In addition to RPA, we can use the generative AI to automate the functionalities, right? Digital twins, especially to simulate any working condition for testing and analyzing what if scenarios, right? Supply chain, we can use it for supply chain optimization, right? Quality control and visual inspection. This is the area which I'm right now working on, where we are using cameras to measure the dimensions of the parts, which the router table does a cut, and also we count the number of objects in the racks, and also we use vision for manufacturing the operations which is being done in a warehouse. And one of the straightforward use case of generative AI is the management of the knowledge-based systems, right? So usually your the maintenance manuals and the SOPs, right? All those things can be fed into generative AI, and someone can query it using natural language. Okay. Smart manufacturing use case, right? Let's see how we can use generative AI for doing a product design, right? I've taken some simple example here. Design a pair of spur gears for 1:2 speed reduction. The input shaft rotates at 2000 RPM and it needs to transmit 5 kilo power. And use steel AISI 4140 as a material. Let's see, let's feed into an chatbot or AI and see how it outputs. So we have asked a question to the AI, and AI is giving an answer. So it has come out this with all the calculation. So it has given module 3 mm, T equal to 60 mm. So all those parameters are needed for design a spur gear, right, for the given requirement, right? It has provided a result for us. So this is the power of generative AI, right? Because it is able to give this result because the model has been trained on the design data earlier. Okay. Okay. Now let's try to do another sample. Create an image of pair of spur gears. Okay, with 1:2 speed reduction, the input shaft rotated 2000 RPM. The same thing, right? Let's try to visualize it. There has been a rapid change in the model updation, right? Frequent change. And you might have recently heard about the nano banana by Google, right? So the technology is advanced so fast, and it's a generative AI, and it may also make mistake, but it's very handy if you are going to do some POC or trying to get some alternate or trying to present to someone, right? So when you visually present it, it's easy for everyone to understand, right? It's quite handy too. So it has generated an image, right? So you want to refine this design, right? So they say the previous spur gear has too much backlash, so we just need to adjust it. We'll ask the AI to refine the design. Let's see how it does. And also we're asking the AI to recommend for a hardening process. So the previous spur gear design has too much backlash. Adjust the center distance or profile shift to reduce backlash to under 0.05 millimeter. Also, can you recommend a surface hardening process for the pinion to increase wear resistance? So let's see what the AI responds back. So this is a power, right, which a single man company or a medium and small enterprises, right, they get, right? They don't have to have an expertise to design a best solution. They can always rely on AI. So it has come up with its own recommendation. Apply a small positive profile shift. Reduce assemble center distance slightly. So also we have asked for the surface hardening, right? We got some surface hardening recommendation as well. Induction hardening, it recommends induction hardening. Apart from that, it also suggests carburized nitriding. It's not only that, right? So come up with an architecture, right, where the generative AI can be applied on for the smart manufacturing, right? If you look at here, right, we give input prompt. Input prompt is the requirement which we give. So input prompt is nothing but a natural language requirement which is specific to the model. So there is a separate topic called prompt engineering, how to best specify the prompt into the LLM, right? So the whole idea is we need to provide the entire context to the LLM so that it can have the understanding of the requirement and can provide a better result to us, right? But if some companies, right, they have their own design engine, they have their own data for materials that needs to be used, right? They can be augmented here. That's why I put here tools, right? LLM has an option to call tools where the specific functionality can be handed over to it. Because LLM, right, it's trained on vast amount of data, but may not be specific to the level of accuracy we are expecting for a product design. Some in-house, they already have a software which produce a high level of accuracy. We can augment that data with LLM as well, right? Here, what we have done is we have augmented the in-house standard engineering properties data, and if they have any generative design engine, we can integrate that, augment that, and if they have any CAD capability for generating drawings, we can augment that as well, right? And then take the output and once again feed it to the LLM, right, to get the massaged or a cleaned final result output. So when a generative AI system is equipped with additional capabilities like engineering properties, right, what it does is what it enables us use smart material selection, safety checking, with generative AI design, optimization, performance driven shapes, all the benefits we get. And if they also have a CAD or scripting API access that can be integrated as well. We can get a real-time 3D model creation as an output from the system we set up. So if you augment, it's very well can be augmented with the existing system and it enhances the overall output. That's the whole idea here. So the result of using generative AI, right? Smart material selection, safety checking, optimization, performance, real-time 3D model creation. Okay. Let's see how generative AI can be used in the predictive maintenance, right? How the generative AI predictive maintenance differs from the traditional predictive maintenance, right? Traditional predictive maintenance focus on when and what has happened, whereas generative AI, like, focus on when, what, why, and how to fix it. It goes 2 level up, right? And the data that needs to be needed for the traditional predictive maintenance, right? Or mostly structured data, which means the data from the sensor, we need to clean it and give it to our model, build a classification model or predictive model, and then get output of it. Mostly what has happened. But for the generative AI, right, it doesn't matter what data you have. Even if you have text data, voice data, right, you have some images, everything can be fed and the model understand everything and can give you an output for you, right? One of the major drawback of the traditional predictive maintenance system, right, for certain failures, right, to predict, we might not have the data at all. If and only if we have the data, we can train the model and we can predict the failure. If we don't have the data, if in the past, if the failure has happened only once, it's very difficult to predict in the future because we have only one set of failure data. But with generative AI, right, we can generate synthetic failure data. That's a great advantage here, right? You can create some millions of failure data and you can train the model. Now the model can handle very well, very efficiently. With respect to the automation level, right, the traditional predictive maintenance, right, support up to some level of automation it supports, whereas the generative AI predictive maintenance support higher level of automation. So let's analyze some of the maintenance log with our LLM, right? Let's take for an example, right? Tool number 5. This is a CNC log, right? Or CNC log says tool number 5 stickiness. This happened 3 times in last week. Slight motor temperature rise during longer jobs. And then the technician notes that arm sluggish under heavy tool loads. This is the data we have. So let's see what our LLM says. So we can give this above as an input and ask, given these entries, what's the probable issue and how should we act is a question or the prompt we give to our model, right? And the model says, tool changer where is likely, consider lubricating, right? It gives a solution, consider lubricating or inspecting the ATC server before the next heavy cycle. Also, historical data suggests an 80% chance of jam recurrence in 10 hours. So here is where the predictive maintenance is coming on, right? It says 80% chance of jam recurrence in 10 hours. So with these details, right, the maintenance person or person can take action, whatever is prescribed by the AI system. Okay. So generative AI augments the existing ML pipelines. What it means, ML is machine learning pipeline, right? So if you look at a machine, it might have some 10 sensors, okay? And 10 sensors constantly feeding the data into into the server, right? And if you have some 100 such machines, 100 into 10 sensors, right? Constantly feeding. We cannot constantly feed all the stream into an LLM and get an output of it. So what we do is we create a big data system, feed the data there, get an output, get a summary of the output, feed the summary into the AI system or into the LLM and get an output and work on the output. Okay. So this is another example I have given, right? Coolant pump, it has some various sources, coolant pump failures, and then it has historical failure logs also. We have got spindle bearing failure, coolant system clogging, tool changer jams. So we are asking generative AI to summarize what is likely to fail next and recommend a service action. That's the question we are asking with all the data we have. So the output what we are getting is based on the coolant ramp behavior over the last 18 cycle, there is a 72% chance of failure within 10 operating hours. So there's a 72% chance of failure within 10 operating hours is a recommendation from the AI system. So based on this recommendation, right, we can take action so that there is no downtime or we can reduce the downtime of the machines. So I have come up with an architecture how to implement generative AI for predictive maintenance. Right, this is this. Right, the whole idea is we should have the data fed into the system. So collect the data from logs, sensors, missions, everything. And because the data is huge, we cannot put all the data into the AI system. It has its own token limits, right? So we cannot put each and every GBs of data into the system and ask query on it. So instead, we build our own system, our own pipeline using big data analytics, push all the data from the sensor into the big data analytics system, build the ML model there, get the output from the ML model, summarize the output. Now we put it into general AI system. Now the gives a enhanced result from all the data what we have collected. So once we have the output from the AI system, right, that can be notified to the maintenance department, who is responsible for that, they can take corrective actions. And yeah. And one of the straightforward use case with the generative AI is, right, using natural language to query the content, right? So if you look at any of the manuals, right, or what is new CNC mission, the manual comes with 3,000 page, and they gave a PDF for it. And if you want to go through how to attend any of the issues, right, you have to search for the particular keyword, and then you have to get output of it. Instead, if you can give the PDF to the LLM, right, you can ask a query in natural language. Hey, this failure has happened. What is the remedy for it? How to fix it? And it becomes more valuable, right, if we expose such a system to the person who is working or who is attending the issue on those missions. As I said, these are all proven architectures, right, which is right now used in the industry for querying huge volume of data from the LLMs, right? You can ask the whole idea is you can ask the query in a natural language so that we can get an output. So we got to create here, we got to collect the data, create a vector embeddings out of it, and then query the vector embedding, get those results, consolidate the result from the vector embeddings and put it into an LLM, and we get a final output there. The whole idea of not giving the whole content to the LLM is because there is a technical limitation. We cannot put the entire data into the LLM. So we are breaking the text, and we are locally processing it by creating the vectors and then doing a semantic search there. And then we are only putting those data which is relevant for the query into the LLM and getting an output of it. Right. So this can be used for even for the standard operating procedure, right? You just want to know how to, what is the process for this job, or what is the next step to the job. Usually there will be a routing sheet or a database where you type that part number and then you ask for the next step or next standard operating procedure. But if you connect with an generative AI, right, you can ask a natural language question, and it can retrieve answer from any part of the source, right? If in the PDF, if the first page has some data, first page has some answer, and the 1,000th page has some answer, and 1,500 page has a little bit of answer. When you put into an AI system, right, it retrieves those data from those pages and you present it to us. So it's a huge advantage there. This is pretty much I want to share with you. Open to any questions, any queries you may have. Any questions? Any feedback?
Shankar.
Hello, sir.
Yeah, sir. Any queries, any questions, anything you understand, anything you don't understand? How is it?
Participants, any questions?
Participants, and small information regarding the Saturday session. Instead of 2 o'clock, 15 minutes earlier we start the session, right? Because the expert is having another program on Saturday, so that instead of 2 o'clock, we'll start by 1:40. Am I right, sir? Gopi sir, am I right?
Yes, sir. Yes, sir. Correct, sir.
We are starting by 1:45, yeah?
1:45 p.m.
We are starting by 1:45 and the session closes by 2:45. 15 minutes earlier we are starting, right? So please stay connected. Tomorrow there is no any change in the session. Tomorrow, as planned, we have 2 sessions tomorrow. One is by Dr. Satish from Anna University MIT campus, and another session is from Dr. Shivashankaran. He is from Quasi University, I think so. Just a minute. So day 5 tomorrow, the first session is by Dr. Satish on the title Synthesis and Characterization of Functional Nanomaterials. This session will be very interesting. And the second session is on design, fabrication, characterization, and mechanical performance of thin wall metallic components using wire arc additive manufacturing process. This session also will be very interesting. The expert of the second session is with Dr. Professor S. Shivashankaran, and he is from Quasi University, Saudi Arabia. Okay, so there is no any change in tomorrow's timing. As it is, the session will start at 6 p.m. and it will end at 9 p.m. And only there is a small change in Saturday session. The Saturday, instead of 2 o'clock, it will start by 1:40, 15 minutes earlier, right? Other things remaining the same. The expert also is remaining the same. So thank you very much. If you have any queries, you can ask now. So thank you all for being patient. So here we are having some network issue today only because of heavy rain here. Tomorrow, I think there won't be any disturbance in the network problem. Okay. Thank you very much. Gopi sir, you can close the session.
Okay, sir. Sir, Manohar sir, shall we close the session, sir?
If you don't have any queries, we can close the session. Nobody had any
Participants,
queries.
do you
So
have any questions? Please ask Manohar sir.
Participants, if you please enable your video, we'll take a screenshot of that. Thank you all. Thank you very much. Thank you, Professor. We'll meet tomorrow. Thank you all. Thank you very much.
thank you.
Thank you.
Sir, thank you. Thank you, Professor. Thank you.
Thank you. Thank you.
Thank you, sir.
Gopi sir, shall I leave the session? Gopi sir? தண்ணி பாட்டில் என்ன எடுத்துக்கப்பா தம்பி. நீங்க சாப்பிட்டுங்க, நான் வெளியே போய்க்கிறேன். இந்த பையன் ஏரிஸ் பையன் இருக்கு அப்படியா? டேய் போய் சாப்பிட்டு போ. நீ 4 பேர் 4 பார்சல் சாப்பிட்டு
அவங்கள போக சொல்லிடுறா.